today we discuss about Compton effect. So first of all, what is a Compton effect and what is the derived expression of Compton shift in wavelength of scattered photon. First of all, Compton effect is an experiment where we prove that the light has a particle nature, and when X-ray falls on a matter, a part is scattered without any change in wavelength. This is known as unmodified or coherent or classical scattering. Compton used Bragg's crystal spectrometer discovered that in addition to classical scattering, in which wavelength of X-ray remains unchanged, the secondary radiation contains X-ray of lower frequency or longer wavelength than those of the incident beam. So this is known as modified or incoherent scattering, and this phenomena is also known as Compton effect. Is very important in quantum mechanics. And the electron, in such a case, the electron is also ejected with an energy depending upon the direction, and electron is known as a Compton recoil electron. First of all, there are some points which you should in mind, that X-ray of frequency nu and wavelength lambda consist of photon of energy E equals to h nu and momentum P equals to h by lambda, that is equal to h nu by c also. This is P equal to h by lambda is basically getting from the de Broglie wavelength concept. And point number two is that the electron assumed to be free and stationary, and it is because binding energy of the electron to the atom is of order of 10 electron volt, which is very small compared to the energy of X-ray of photon, which is order of 10 kilo electron volt, and the kinetic energy of the electron being the same order as the binding energy of the comparatively at rest condition. Number 3 point, the collision between the high energy photon and the electron is elastic. Okay, so the energy and the momentum carried out the scattered photon and the recoil electron is governed by the law of conservation of energy and law of conservation of momentum. So first of all, here we present our Compton experiment. This is an incident photon. Okay, this is an incident photon. This is hits in the molybdenum crystal. So this is the perpendicular direction, and this is the horizontal direction. Okay, this is our incident photon. This is incident photon direction, and this energy equals to h nu and momentum P equals to h nu by c. And here when it hit the molybdenum, so electron at rest, therefore energy equal to m0 c square, and but momentum equal to 0. So now after hitting this molybdenum, it's emit two part. Number one is scattered photon, which energy equal to h nu dash, energy E, and momentum P equals to h nu dash by c. And here energy equals to mc square. This is a recoil electron, this is an recoil electron, and momentum equals to m into v. So the horizontal component is h nu dash by c cos phi, because this is the angle of phi and this is angle of theta, plus mv cos theta according to the vector law, and this component equals to h nu dash by c into sin phi horizontal component, and this component is represented as mv sin theta component. Okay, so now this is the Compton experiment using the diagrammatically representation. And suppose an X-ray of photon nu of frequency nu and energy h nu collides with an electron supposed to be at rest in the target. A part of this energy is imparted to the electron, which is ejected with a velocity v in a direction making of angle of theta. So this is a making angle of theta with that incident of the X-ray photon, and the remaining energy gives out as a scattered photon. So this is the the remaining energy of X-ray photon of lower frequency of nu dash. So now we apply our two principle of conservation of energy and conservation of momentum. So first of all, we apply the conservation of energy, principle of conservation of energy. So here incident photon energy h nu, and this is the electron energy m0c square. This is equal to because the collision is elastic collision, so this is the scattered photon energy plus mc square. These are equal electron. Okay, so this is an energy conservation law of energy. So from here we get this h nu minus nu dash plus m0c square. Okay, so squaring each side, in the both sides squaring, then we get this h square, this is nu square minus 2 nu dash plus nu dash square plus 2h nu minus nu dash into m0c square plus m0 square to the power 4. So this is basically equation 1 presentation, and number 2 is a principle of conservation of momentum. So before hit the photon particle, the momentum is h nu by c. Why? Because this is a momentum of incident photon, but that is X-ray, and after hitting, there are two parts. One is this and another part is mv cos theta, and if we solution of this equation, therefore we get mv c cos theta h nu minus nu dash into cos phi component. So this is the equation of 2. Now this is a horizontal part. Now the perpendicular part, the vertical part, there is a no momentum of incident energy because there is a no, and but after scattering, the horizontal part is h nu dash by c into sin phi minus sign, because this is in the positive direction, this is in the positive direction, and this is in the negative direction, or we say that these two components are in the opposite direction. So from here we get mbc sin theta equals to h nu dash sin phi. So this is equation 3. So now squaring equation 2 and 3 and then adding. First of all, here I mentioned that squaring equation 2 and 3 and then adding, and we get m square v square c square equal to h square nu square minus 2 nu dash cos phi plus nu dash square, this nu dash, this is nu dash square cos square phi plus nu dash square sin square phi, and after solution of this equation, m square v square c square equal to h square nu square minus 2 nu dash cos phi plus nu dash square. So this is equation 4. Okay, and then subtracting equation 4 from equation 1. So that is 1 minus 4 from equation 1. Then we get another equation, that is m square c square in a bracket c square minus v square equals to minus 2 nu dash h square 1 minus cos phi plus 2h nu minus nu dash m0c square plus m0 square to the power 4. Okay, so from here, after some mathematical derivation from this equation, okay, we're getting this term 2h nu minus nu dash m0c square is equals to 2 nu dash h square 1 minus cos phi. So after some again mathematical derivation, we get 1 by nu dash minus 1 by nu is equals to h by m0c square 1 minus cos phi. So now if we take one, here we add one c, then therefore this is not a c square, this is c. So this is another mathematical term. So now c by nu dash is basically lambda dash minus lambda. This is called the delta lambda, that is Compton shift in wavelength, that is equals to m0c 1 minus cos phi. Okay, so this is very important. This delta lambda is also known as Compton shift in wavelength and is known as the Compton equation. And this is a Compton equation that increase in wavelength or Compton shift delta lambda is independent of the wavelength of the incident radiation as well as the nature of the scattering substance, but it depends on the angle of the scattering, that is phi. Okay, now we derive some term here. H equals to Planck constant, which is equal to 6.624 into 10 to the power minus 34 joule second. Okay, and m0 is the rest mass of the electron, 9.1031 kg, and c is the speed of light, 2.998, that is equivalent to approximately 3 meter per second. Okay, this is the parameter, and when we put in this formula, then we get 0.0242 Armstrong. Okay, this is known as, this is one important parameter, and here delta equals to 0.0242 1 minus cos phi Armstrong. Okay, so this term, this is very important term, h by m0c. This is also known as, what is the parameter? This parameter is also known as lambda c, that is Compton wavelength. It's very important for examination and competitive examinations. Okay, now we look here, if phi equal to 90 degree, then delta lambda is 0.0242 Armstrong. But phi equal to 0 degree, then there is a no shift in wavelength, that is 0 degree. Okay, there are several terms, several conditions depend on the different types of angle of scattering. When phi equal to 30 degree, say 10 degree, say 20 degree, say 40 degree, different types of values of phi, we getting the shift in wavelength, length lambda. So that is the importance of Compton theorem, Compton shift in wavelength. Okay, so this is very important, Compton shift, and is for the quantum mechanical behavior of the particles. And this experiment also show us that light has a wave nature, because here wavelength phenomena, because here wavelength changes. So now we discuss about, here we plot one chart of phi versus delta lambda. So from 0 degree, from 10 degree, from 2 degree, 20 degree up to 90 degree, there are several different types of shift in wavelength are showing by this Compton experiment. So this is a mathematical derivation of Compton, and this is one picture by which the Compton experiment will be shown, and how the X-ray will be scattered by the rest of, supposed to be a, and X-ray of photon of nu and energy h nu collides with an electron supposed to be at rest in the target. Okay, so this is the experiment of Compton effect, also known as Compton effect, and expression of Compton shift and wavelength of scattered photon.